Of course, AI agents are pretty powerful, but there's one big problem, which is they cannot learn. But what if we can keep training our AI agents as we use them so they will keep learning from their previous experience of failures or success through reinforcement learning? And yes, this is feasible thanks to this recent paper published that they're talking about a multi-agent collaboration via evolving orchestration, and that evolving piece is happening through reinforcement learning. So as we use our multi-agent frameworks that we are creating them through our use cases, they are getting better and better through the progress of usage. So in this video, I'm going to talk about this approach and obviously show you in action through a demo so how we can utilize this and see the progress through reinforcement learning. So stay tuned. For the beginning, let's see what is the initial challenge that this paper through multi-agent collaboration via evolving or reinforcement learning orchestration is trying to resolve. Well, as of now, when you create your multi-agent systems, you might potentially have a sequence of multiple agents that agent A does something, pass it to agent B, C, and then finally the result is there. Or even for more complicated scenarios, you might define a master agent or orchestrator that agent will call other agents or one agent based on the type of inquiry that is needed. And this is how you define how that master or orchestrator agent should work. You define the rules instead of prompts or instructions. And you might say, well, this is good enough, but for complex scenarios, specifically when you have lots of agents and tools, this is pretty challenging. The agent won't be able to properly define what other agents should work. And obviously that might be waste of token as they collaboratively try to figure out which agents should do the work. And then the adaptation of that will be challenging and poor performance obviously comes after that. So in this approach, we are trying to resolve this, which they call it through puppeteer paradigm. Well, puppeteer is like when you have this puppet being handled by multiple orchestrators. So think about it. When we have that main orchestrator agent in your framework that choose a task, this time we don't have any orchestrator agent. We might have just one reinforcement learning, which we call it here puppeteer. And this one will define which agent or agents should do the task. From the beginning, it has no clue because there is no orchestrator. There is no prompt or there is no instruction. But as long as it starts to work through our maybe training data set of what agent should be called to get that desired outcome, then through this reinforcement learning, it will understand that, okay, for this MG's question, I should call maybe planner and then refiner and then coder. That's it. It goes exactly to the point of the path without us instructing which agent should be called and when. This is the main value of this approach. Alright, when we talk about reinforcement learning, then we are talking about state, reward, action. So how this is defined in multi-agent system here? Well, obviously at the beginning, we should observe the state. Think about like chess game. When we have reinforcement learning that are gonna understand chess move and do that through AI, it should understand what is the state of the game. Same thing here. We should analyze what is the current state of our multi-agent system, which agent is working now, what previous agents worked so far, and what are the findings before we get to the final goal of resolving a task by this multi-agent system. Then on the top, we're going to decide, okay, based on this status, what is the next agent I should select? For that chess game is like, what's the next move I should select? Then after that, the agent going to act, do something, make a change, make a move, and then we need to update the overall state of, okay, the new agent just got selected, executed, and here's the new state. Figure out, okay, what is next? Are we done, or we should move with more sub-agents to finally resolve the task? So in initial state, because we have no orchestrator agent to tell us which sub-agent we should call, it's totally random and initialized through some random equal chance of setting up those sub-agents. But as we iteratively through reinforcement learning give some tasks, let the agents work even in random state, come up with the final answer, we are going to evolve and come up with a dedicated path if a similar task will comes after, so we know which sub-agent should be called, because we have reinforcement learning here that it is adapting itself as we through these tasks and get to know what is the final outcome. So initially, right now in your use cases, you might have some tasks that you call your agent A, B, C, D in a sequence, but through this reinforcement learning, it might come up with a whole new type of sequence. Yeah, maybe first call agent A, then agent B, agent D, again agent B. So we never know what's going to be the sequences because the task and use cases or questions would be different for this multi-agent system to work. And that's going to be the job of reinforcement learning to figure out how these sub-agent should be called. And good news that efficiency of calling which sub-agent when and how will get better and better as we use them. This is extremely powerful. So to show you in action and implement that through vibe coding, I actually developed a demo that apply a simplified version of this solution that they're proposing in the paper. So what we're going to do here, I have actually created a multi-agent system. Let's say there's an IT system and there's an incident coming in. And instead of a human figure out what is that incident and how to resolve for IT, we will have 7 agents, sub-agents, I would say, to do the task. And we don't know which one should be called. I'm not going to prompt a master agent to define which agent should be called. Maybe I have something initially defined, but I want to have it improved through reinforcement learning. So I have 5 training type of tasks, which when I have, there's a caching issue, there's a database issue, there's an API issue. So we will see that in the code that these are my initial incident. Then that puppeteer or that reinforcement learning try to understand which agents should be called, which we call it agent path. And afterwards, how would you reward that through reinforcement learning? If the final answer is resolved, if we understood what's the issue of that IT incident, that's 1 score. If we identify that root cause issue with less number of agents, that's additional reward. If we get to that successful outcome with less tokens, that's also another success. And the opposite of all I just mentioned is penalty. This is what we define in reinforcement learning. And then as we go, we update the reinforcement learning policy parameters, which I'm going to show you to have this get better and better. Maybe in the initial episodes, we have lots of mistakes. Within the middle, we will get smarter orchestrator, which is reinforcement learning. And after that, we will have the optimal path of which agent should be called for given task without having any prompt to define that which agent should be called. We talked about reward and penalty, but what about the state? So for state or situation of this multi-agent demo, well, I'm gonna have, first of all, tell me how many agents has been visited so far. This is like chess game to see what moves has been made to define the next move. Then what's the confidence of these agents so far? How do we define confidence? For this demo, I am catching some keywords in agent answer. If the agents say definitely, for sure, then confidence is high. But if it say most likely the issue is this and that, the confidence is low. For even a better scenario, I can use an LLM to define what's the confidence of this agent which is giving me the answer. This is the state that I need to know through reinforcement learning to make the next move. On the top, how many tokens have been used? Ideally, the less the better, but so far I want to know how many tokens have been used to define the current state, then to make the next move through reinforcement learning. And did we find the root cause? If yes, then we are done. The state is finished. If not, okay, we need to continue. Did we get any error detected? Did we have cache issues? Did we have database issues? Why do we need to know that as a state? Because these will be helpful to define what is the next actually agent. If there's a cache issue, maybe I should call cache agent to resolve that for me. And as we go, we update the state through reinforcement learning. Again, obviously at the beginning, we might have some random agents, random path of the agents to be actually selected, and we might get to the final point of resolving the need and finding the root cause for IT, but maybe in a very long or not really efficient path of choosing agents. So as we go, we follow best paths, we maximize efficiency to achieve the goal, which is root causing the IT issue. But this time, that brain, which is the reinforcement learning piece, would say that I know what works and what's the best path of resolving that upcoming incident for IT. All right, so how do we score success? First, if we found the root cause, score. If we increase the confidence of those sub-agents, that's a score. Did we find relevant issues? That's another good score. And if I use too many tokens, that's a bad one. Similarly, for another scenario, we're going to do this all end-to-end again as we choose sub-agents to finally calculate the final reward based on how we have made progress to calculate the final score through this sort of equation. Of course, we're really simplifying that, but just want to give you an idea when we talk about reinforcement learning, what is the reward and penalty here that we are discussing. All right, here's my quick sample demo code. I have created a Simulate app, so it has UI, but just want to show you a little bit of backend to have a better understanding of what's going on in this demo. As you can see, I have 5 different type of instances that I'm defining to test and also use it for initiating and training that reinforcement learning. I have, let's say, incident ID, and I know there is a cache failure. And what's the issue? Well, there are so many high memory usage on cache servers, and these are the symptoms. So potentially this is going to be a root cause. So we know the answer. And the complexity of that would be simple. I have some complex scenarios, so I want to challenge this reinforcement learning based approach later on. So these are some sort of initial incident that I have defined here, and obviously some system metrics that I'm hard coding that because I'm just using for demonstration purpose. So let me show you the agent. For defining the agents, I have used Google ADK for a framework of defining my agents. You can use LangChain, Llama Index, like literally anything. This approach is totally framework agnostic. So I have a monitor agent that defined the initial system health monitoring. It used a function that retrieves some system health. Same thing, I have a log analyzer agent. I have cache expert that when there's a caching issue, this agent might be called. There's a database expert, API expert, dependency analyzer, and then resolution agent. And obviously these are the list of agents that I can use that I showed you. And as you can see, there is no orchestrator agent. There is no master agent to define which of these agents should be called. We're going to do that through reinforcement learning. So without reinforcement learning, I need to call maybe all these 7 agents to get the response back for that incident, which might work and give me the final outcome. But I want to see with reinforcement learning, maybe I can drop it to 2 agents or all of the agents or 6 agents based on the type of the use case and the challenge of that incident. So reinforcement learning is going to do that for me. Let me jump into the actual UI. But before doing that, I'm going to quickly show you the function that I use for reinforcement learning. So RL or reinforcement learning by itself is a whole dedicated topic. I'm not going to go through details of that. But here you see that I have a class defined, which I call it puppeteer policy, or this is the reinforcement learning for having that as a main orchestrator. I need to initiate my initial state that I have for the agents. And you can see that I have some learning rate that I'm going to adapt this policy, which is theta, as I move forward with understanding what is the state of the current multi-agent system, what is next. Are we getting closing or we're getting penalized because of all those rules that we are defining that I told you about? And then we need to also get what is the action probability based on this state and the theta that we have updated through the policy. And then we select the agent through this function. And obviously we need to also do some exploitation. These are again specific components of reinforcement learning, which I have defined it here. It is really a basic, simple implementation of that. So it's really not an advanced one. Again, I'm doing that for sake of demonstration. So let me show you the UI, which might be fairly easier to discuss that in action. All right, here's the Simulate UI. And as you can see, I have multiple incidents that I showed you in the code that has been selected. For example, incident number 2, there are some database issues and we have these symptoms. So what I did, I just actually let me run through traditional, and I want to run through this new puppeteer approach to see how they're working, given that I haven't trained my reinforcement learning or this puppeteer approach yet. So when I click on run, it is running right now. And when the result is ready, it's going to show me actually what's the difference of finding this answer using traditional approach, which is maybe calling all the agent, versus the one that use reinforcement learning that has been not trained yet. So I am expecting that still our traditional approach of multi-agent system is better because this one hasn't really learned anything and it's just maybe randomly selecting some sub-agents to figure out what's the issue with this incident. So let's see what's going to be the answer. There you go. It's just done. If I scroll all the way down, so on the left side, you will see that sequentially we had all these agents called for me. Initially from this log analyzer, then calling database expert. So how many agents? 7 agents. All of them are used. With this amount of token, obviously we found what's the issue. But on the other side, because we haven't really trained this reinforcement learning yet, it has used even more agents because a couple of them were called more than once, like this API. And you can see the sequence is much lengthier. And then it found the answer, but with much more tokens. So not efficient at all. Now we're going to see if I can figure out this reinforcement learning to learn from this mistake to even come up with the answer with even less than 7 agents like this one to improve without having any master agent, which is this reinforcement learning job to do it for me. So for training that, if I click on the training, obviously these are the parameters that I need to have for reinforcement learning. I want to go with training epochs, with this learning rate, and with this initial exploration. 30% exploration means that 30% of the time do exploration to understand and then exploit your understanding on 70% of the time. So I want to keep it as is and start training. To just show you something quickly on the learning process, I haven't done any training now. That's why it's empty. So if I click on training, it will now start training with multiple epochs that I have here. As it's gonna take a bit of time, so I'm gonna pause recording, but the result of the training will be saved in a pickle file in my local machine, so I will be able to see the learning process and also rerun all those tests to see this time how reinforcement learning is choosing the sub-agents. So I will come back to you shortly. Alright, the learning process is over. Obviously, if I let it continue, the result will be better and better, but you can see that my average reward, it was fluctuating a little bit, so not that good at the beginning. Then I got some really good high rewards as I was going through with further training epochs. And gradually, still there are some fluctuations, but the overall trend on average, which is the red line, is sort of upwards. That means I am in the progress of creating a better reinforcement learning and more accurate solution, but it was taking a bit of time. This one took like 20-25 minutes. And for this is just for sake of demonstration. I don't want to continue further, but that's the whole idea. So we are making some progress here. And now if I go back to that initial live comparison that we did for incident number 2, this time, this reinforcement learning, although it's not that good yet, and it has room to grow, with just one agent, it was able to get me the answer with much more token compared to the previous traditional one, which used all of that agent. You might say MGI can still use one master agent here to define which sub-agent should be called, so why you're calling all the agents? You are right, but still remember, for complex scenarios, especially if you have large agents, having just one master agent to define which sub-agents should be called is not enough, and I'm pretty sure you have been in those situations. That's why that reinforcement learning approach that learned through these training experiences will be potentially more feasible. And as you might say that, okay, we have learned some stuff here, but in general, how that approach worked with all the training samples that I had. So I had sort of 5 training incidents that I showed you, and I ran this new reinforcement learning on all of them. And on average, this new reinforcement learning approach used much more less token, and much more less agents were used compared to traditional one, and the success rate of both of them were 100%. So I can clearly see that this approach is much more robust based on efficiency, although both of them give me final okay answer. But look at the difference on average number of agents used versus average number of tokens without having an orchestrator agent here, which is extremely powerful. So to a little bit further, having further understanding about this, what we have learned so far, I have actually now a pickle file that I will show you right now, which is in my local environment. That is actually here. As you can see, I have this policy pickle file uploaded for me. This is actually those theta parameters of the policy of the reinforcement learning. So whenever I load this multi-agent system, that table going to be referenced, and it will use to figure out which sub-agent should be triggered based on the state of the system. Now, let's have a little bit explainability on what is that pickle file and what we're trying to do. So this is the policy parameter that we have learned for choosing a specific sub-agent on the given situation. I have 7 features here from 0 to 6, which is 7. And these features are the state of our multi-agent system. For example, feature 0, or which is here noted as 1, says how many agents we have used so far. What is their confidence score? How many tokens we have used? What is the root cause of that? Do we have any error keyword in the answer so far? Do we have any cache keyword? Do we have any database keyword in the challenge? So, and this heat map says when we have, let's say, database keyword, which is last feature here, for agent resolution, it's not that important. but for monitor agent, it is more important. So select monitor agent. But for example, for let's say this one actually, resolution agent, you can see that feature number 0, which is number of agent used, is the less important one for this resolution agent. So that means when you haven't used any agent yet, and the number of agent is pretty low, for example, maybe go with resolution agent. The other one, for example, this one, log analyzer. This one, it cares more about the number of agents that has been used. So this is a little bit of understanding when this system based on reinforcement learning is choosing my agents and how much they care about which component of the state to choose one of these sub-agents. Or when we talk about a state, for example, when we have initial state that we have totally no context of what's going on, we just want to start calling the first agent, the probability of calling any agent is almost the same. But in state number 2, as an example, when there's a caching issue we have identified right now, then the probability of having maybe cache expert is higher compared to the rest. Another example here, when we have a complex scenario, the probability of using monitor or log agent is less, but the probability of calling these expert agents is higher. We have learned that through calling the reinforcement learning system multiple times to update this policy parameter data and choose the sub-agent based on where we are with the given state of the system. All right, that was the video about this new paper that I just came across that, and I found it's absolutely impactful to come up with a new way of combining reinforcement learning with our multi-agent systems to let them sort of, I would say, in active learning, not really, but it's still, instead of just us prompting static instructions of which sub-agent should be called, now we have a system that continuously learns as it makes mistakes. I hope you found this video helpful. If yes, I would be very thankful if you can like icon and share your thoughts in comment sections. And if you feel like this demo that I created is helpful and you're in need of getting the codes, let me know. I was thinking to just have this code as for demonstration purpose, but if it's helpful, write down in the comments that MG, let's share this code. I will add the code for sure, and I will add that in the description. And please make sure to subscribe so you won't miss the next video. Thank you so much.